All right, so if you have a system and you have a force on it, right, that force is doing a few things to the system. One of the things is what? What's this 10 Newton force doing to that system? What's it trying to do? Push it down, right? So that's what I call a translational effect, or an effect in the y direction, right? And if we put more forces on, then they're trying to do maybe something in the x direction. If we get a force at an angle, it's trying to do something in both x and the y direction, okay? So I think you've done some of that, right? You've collected forces in the x, you've collected forces in the y. Have you done resultants of that? Like figured out what the total effect is? Perfect. So now with this couple thing, these things are also trying to rotate the system, right? They're trying to spin it. So if we choose point A, this 10 Newton is trying to do what to point A? Yeah, rotate it like this, right? And this one's trying to rotate it like this. So that's what this couple thing is doing for us, is it's collecting the rotational effect. And when you do them individually, you just do moment, force times distance, right? We take the 10 times this distance and we can come up with that rotational effect about point A. So this system looks a little different than this system. Have you guys done some of these? Yeah? So do you remember what this one's called? That's a free body diagram, correct. What kind of a force system? It could be an equilibrium. If we went down the road of equilibrium, concurrent, all the forces through one point, right? Did you ever talk concurrent, non-concurrent? Yeah, so the book mentions it somewhere, but like maybe it's not emphasized. But that's a different system than this, right? This has forces not all in one spot. So to get to the single force here or the single effect, how did you do this? This concurrent system. Anyone remember? This is good. This is good, like, to remember. Like if I want to say this is the same as like this, how'd I get there? Yeah, add the forces together. How'd you do that? Components was one way. Was there any other ways? Yeah, like the whole graphical method thing, right? Yeah. So that's how you did that. That's how you took this force system to a single effect, right? So we have to be able to do it with this kind of a force system too. This is non-concurrent. Concurrent, it's like Newton's laws. Like it's either in equilibrium or it's not. He got two laws out of that. I think that's bogus. It's really just one law. But this, right, concurrent, non-concurrent. So the way that we solve these down to the single effect, which is kind of the end goal, this reduction of this couple thing, is we use moments. All right? That's why we need moments. It picks up the rotational effect, and it allows us to turn a non-concurrent system, this kind of a system, into a single effect. All right. So you have been working with moments, and we know that it's force times distance, correct? And there's a couple ways we can do that. This is still a little bit review. If the vector is at an angle, and I want to know the moment at A, how can I do that? We know it's this equation. Yeah, so we could actually draw a picture. Good comment on the line of action of a force. All right, we could draw this picture, and this could be this, and I put a little perpendicular to it because that's kind of important, right? We could draw that picture, and then we could do like maybe trigonometry and come up with this perpendicular distance. Right? That's one way we could do it. How else could we do it? Vectors, the components. Perfect. All right. That's what I wanted to know if you had down. Or at least you've done some, right? We can turn it into the x and y components, and then we can find the moment of the x and y, add them up, and we get the same value as doing it this way. So there's a couple different ways. Okay? All right. Now, when we talk about this couple thing, that is just a special case moment. Okay? So This moment, when we calculated, it was about a very specific spot, point A, correct? Like we could do it about point B, and we'd get a different moment. Agreed? Everyone with me here? All right. So the couple thing is a special case of forces. And I'm going to draw the simplest couple first, and then we'll get more complicated. The reason they're called couples is because they have the same magnitude. It's two vectors. If you see two vectors with the same magnitude, so magnitude's the same, they must have a distance apart. So they cannot be like this. We have no rotational effect in this case. If we had 50 up and 50 down, that would be like a nothing, right? Agreed? So we must have some distance apart. The magnitudes must be the same, and they must be oppositely directed. So there's got to be three things for the couple. If you don't have all three, you don't have a couple. And when I teach this, I find students are trying to make couples out of things that aren't couples. So make sure, same magnitude, 50 pounds and 50 pounds, 10 newtons and 10 newtons, right? A distance apart. There's no rotation unless we have a distance apart. And parallel. They've got to be parallel. They don't have to be vertical. They don't have to be horizontal. They've got to be parallel. So it could look like this, right? As long as they're the same magnitude, a distance apart, oppositely directed, then you can identify it as a couple. So this first section is just like trying to understand this couple thing and what's unique about it. And there's something really unique about it. So I'm going to just make a basic example problem out of this. I'm going to call this point A, and I'm going to say this is 6 inches, and this is 12 inches, and this is 6 inches. Okay? And we're going to go back to the moment logic that you know already, which is the force times the distance. We know that's a moment, right? So I'm going to have all of you take the moment about point A of this system, if you would. What is the moment about point A? I'll give you not a lot of time because we know that's going to be a force times a distance, right? And we'll do each one, and we'll calculate the total moment at A. And I didn't bring a calculator, so I'm going to totally rely on you to give me good numbers and to verify. I want the moment of A with our old logic, where we just take the force times the distance and a force times a distance. Remember with moments, how do we get their sign? Plus or minus? Rotation, yeah. This one's rotating this way. This one's rotating this way. Counterclockwise is what? Positive or negative? Positive. Clockwise is negative. So, the moment at A, I'm actually going to write it as some moment at A. Hopefully you're on the path here. This is summation, right? We're adding up the moments at A. It's going to be 50 times what for this 50? 6. Thank you. And its rotation is positive, so I'm going to make it a plus. And then for this 50, it's going to be force 50 times what? 18, thank you. And its rotation, negative, equals. Say again? Others agree with that? Yep. Minus 6, what's the unit? Yeah. I say foot-pounds. I just have a hard time with pound-feet. Doesn't roll off my tongue that well. Yeah, so that's your old method of calculating a moment, correct? Yeah? Everyone's familiar with that? Not too bad? Okay, I'm going to have you do it again for me. Same system, but I'd like you to calculate the moment here at point B. Not a trick question. We're going to do moment at B. What do you know about 50 pounds going straight through B? It's 0 moment there, right? So it doesn't even go into the equation. You could write 50 times 0, but eh. And then what about this 50? Yeah, so it's going to be 50 times 12, correct? What's the number? Negative 600. Interesting. What do you think it is if I do the moment here at C? Negative 600. What do you think it is if I do the moment right here at 6.743 inches left of A? Yeah. Anyone seen a trend here? It's the same moment no matter where you take it. So the moment of a couple is not specific about a point, but it's anywhere you want to place it. Whoa. That's completely different than the moment of a force. Moment of a force is about a specific point, but a moment of a couple is, we can move it. It means the whole system has this rotational effect acting on it, or it feels it. Okay? So they occur, like if you think about, oh, I'm driving my car, maybe I'm creating equal force. That's the example they use. Equal force on each side, that's a couple, right? A force couple. So they do kind of occur naturally out there. If you take a wrench and stick it on a bolt and rotate that bolt's actually hitting on 2 spots. It's not, you think it's hitting the whole thing, well, it's not. If you've ever rounded a nut off, you know it's not, right? Like it's just hitting these 2 spots and you just like round it right off if that didn't fit perfectly. So that rotational effect of a socket on a nut hits 2 spots, creates equal forces. It's a couple. Okay? Again, you need this concept to move to the next one, which is all about trying to solve these complicated non-concurrent systems. Because this concept allows us to move forces around because it's going to collect that rotational effect.
Is that amount for the whole line? Go like really far out?
Yep, it can go anywhere. You can go vertical.
Within a certain direction?
No, not within a certain direction. Anywhere. Like if your system is, looks like this, and you have some kind of a couple going on like that, right? So then you can calculate this couple moment and put it anywhere. I can put it up here, I can put it down here, I can put it over here, I can put it anywhere. So again, it's our method of like moving things around. When they come to us naturally, like this, like the first problems you're going to do, they're going to just give you some couples and say calculate it, right? And you'll use your techniques that you've used in the past to calculate the moment of a force. You just do both of them. This is kind of long form, do both of them. It's also, I think the equation they give you in the book is the same for couples, but distance now can be this distance between. So if you see a couple and you want the moment, it's force, one of the forces, this one or this one, times the distance between, if you have it, right? If that's given in the problem, like horizontal and vertical couples are pretty easy because we have those distances between easily. But if it ends up to be, I think I saw you'll do one like this. Thank you. Right? Where maybe we know this is 12 inches from here to here, and we know this is 30 degrees and 30 degrees, and we have, I don't know, 10, oh, not newtons, huh? Pounds and 10 pounds. Right, we don't know the distance between. You could trig the distance between if you want, or you could turn it into what? Components? Right? See any couples there? Yeah. You see two of them? You sure? Careful, only one, because these two what? Don't have a distance apart, and we've got to have a distance apart. So, notice that, and the way I do couples is I do that. I tie them together and say, oh, that's my couple. Okay? And these two would be the same, right? I mean, those will be the same, and that will be the moment of the couple created by these two. Does that make sense? That's just using your component knowledge. So if you get them on an angle, you can do a couple different ways. You could come up with this distance and do it directly, 10 times that distance. Or you can break it into its components and use this 12 and these components and also get the same couple. Good? All right. Now, why the heck? What do we do with these things? Yeah.
If they're the same magnitude but different angles, does that matter?
Not a couple. Got to be parallel. And I don't think I emphasized that in the very first time I said it, but they've got to be parallel. They're not a couple if they're not. Yeah. So all the components got to be equal, right? That's the only way it's going to be. If this was a different angle, then that component would be different than that component. Then it would not be a couple. And we do want to identify them. More importantly, we want to make them. We want to make couples. So I'll show you that next because that's kind of the next section. Once you kind of get what a couple is and that it can go anywhere, then we start to make them to move vectors around the system. And the reason we want to move the vectors around is we want to get them all to one spot so we can add them up, just like we did before. And then we'll know the total resultant of the force system, and then we can actually do some logic with that. When we have a system that looks like this, it's hard to get a feel for what's going on. Like I could put a bunch of numbers on there, and then I could ask you, does it feel an up effect? You'd be like, I don't know. Like if all the numbers were close, it'd be like, I have no idea. The only way to really know that would be to like go through the sum of the forces in the y and the sum of the forces in the x, right? Then we could get up effect and down effect. But as far as rotation goes, like, what's it feeling? I have no idea, okay? So we have to come up with a way to know what this thing's feeling. Is it feeling a big rotation that way or a big down rotation? We have to be able to collect that effect, and that's what we do with these couple things. All right, let me show you. In basic form, what happens? If I have a system, and let's say I have a couple forces on it, 50 pounds, and I'll put 30 pounds, and I want to bring those two forces together and understand the effect. I can do that pretty easily in the y direction. I can think about 50 pounds down, 30 pounds up. What's the effect on this system? Some pounds down, right? It feels some down poundage. But what's the effect in the rotation? I don't really know. And if I wanted to know, I need to be able to combine these vectors, right? You combine them, like if it was concurrent system, then it's super easy. They're combined already, right? But if it's non-concurrent, then there's these rotational effects going on. The 50 has maybe a bigger rotational effect than the 30. They're a little bit opposite of each other. But what's the final effect that this thing feels? That's where we need to go with this couple thing. So around any point, like we can decide, yeah. So if there's supports, it might be we want to know what's going on at that support. If there's like a big span, we might want to know what's going on in the middle. Like in the future, I'll want to know how much something's deflecting. Like if it's supported here, really what I might want to know is like, what's the deflection of this thing? And then at some point I might want to know what's the bending stress. In order to get there, I need to know what the effect is, not the multiple effect. Right now I have two effects going on, right? And just think about any real system might have 100 of these forces on it. Then I'm like, I have no idea what the effect is. I need to figure it out. Okay? So the way we do that is we typically pick a spot And as you go forward, you'll get to where you pick a logical spot. But right now, I'm just going to pick any spot. And I'm going to just move the forces to that spot. I'm going to collect their effect, right? And we know there's up and down effect, but I also know there's some kind of rotational effect. That's this moment thing. The way we can do that is by building couples. So if I want to move the 50 to A, I'm going to build a couple with this 50. That makes sense? And we know what a couple is. It is, give me all the characteristics one more time. We need parallel. So I'm going to go ahead and I'm going to draw a parallel. Opposite direction, thank you. Equal in magnitude, thank you. And the last one was some distance apart. And I picked point A, and I definitely have some distance apart. I need to give myself some distances, so let's do this. Let's do 2 feet, let's do 3 feet, and I don't know, 3 feet. All right, so I made a couple, right? But it's not just, you can't just throw forces on a system, right? That would change the system. Oh, I added 50 pounds up. You can't just do that. So what you have to do is if you're going to add a vector, you have to add another one. Equal in magnitude, oppositely directed. If I add the 50 going up and the 50 going down, did I change the system? No. Those two just, they negate each other, right? It's like algebra. If you're going to do something to one side of the equal sign, you got to do something to the other side, correct? If you're going to multiply by 2 on one side, you got to multiply 2 on the other side. Same thing here. If I'm going to add a vector, I got to add another vector and make it like negate each other. That make sense? But what it did do is it created a couple. And what do I know about couples now? They create a moment, and the moment can be put anywhere I want. So what happens is I calculate this moment, which is going to be what? 50 times the distance apart. What's the distance apart? 5 feet. And what do I get? 250? Is that right? 250? Foot-pounds? Correct? Everyone with me here? I created this here couple. And which way is it spinning? Is it spinning clockwise or counterclockwise? Think about these two. It's going that way, isn't it? Like if you think about arrows in a string and let go of it, it's going to spin like crazy. Does that make sense? So this is got a rotation. It's a negative rotation, but most important, it's clockwise, right? And since that creates a couple, I can now move it anywhere I want, which means this is gone, and I'm moving it here to create what's called a force couple. Force couple. And that couple is 250 foot-pounds, and the arrow is telling me which way it goes. All right, I'm going to clean this up just a little bit. I'm going to let you digest. But the system now looks like this. I didn't do anything with the 30 pounds, did I? I didn't even touch it. But I created a couple out of the 50. I calculated the couple, and then I moved it over here to A and created what's called a force couple. I literally moved the 50. The advantage to this is now I can move the 30 to point A also, and I can add it up. With me? How do I move it? This couple thing. I create a couple. It's hard to do over the top of the 50, but I'm going to give it the old college try here with some color. I'm going to add two vectors of the same magnitude of what I want to move. Right? Didn't change the system. 30 up, 30 down. It's all cool. I can take this table, I can push down and push up. Nothing changes on the table. But then I created a what? Between these two, a couple. And what can we do with couples? This is getting redundant. Andy, I'm being redundant. We can calculate their moment, and we can put it anywhere we want. He might not. We'll give him a code word. Engineer, that's the code word. So then you can ask him the code word to see if he even listened to it. Why would he listen to it? He shouldn't have to listen to it. All right, scratch the code word idea. So what's my moment here in my couple? Yeah, it's 2 feet. 2 times 30 is 60 foot-pounds. Which way is this one rotating? Is that counterclockwise? Yeah? Nice. So these two used the couple, they go away because I calculated the moment from those two into this 60. So now I'm left with, here's my system. I'm left with my 50-pound force. This one is left over. That's the 30-pound force. So that's not news to anyone right there because we could have looked at the original system and said, we have 50 down and 30 up. You all did that, right? But this is what I call the translational effect, or the X and the Y effect, right? So this just collects that for you in the move. That's good because we can't lose that. But then the rotational effect is taken up with we have 250 foot-pounds, and we have this rotational effect going the other way. Oh, I should have made it red, darn it. There we go. Or blue. It's going to be blue down here, so you have to just keep up with that. Right? And that one's 60. Force couples. Force couples. So I think your section 4.6 is like couples, moment of a couple, what the heck is it? We did that. And now we're kind of in this force couple thing, where when you move them, you end up with these systems. But you know how to resolve this, right? The two forces, the 30 and the 50, is add them up. And we're left with what? 20 down, right? Okay. So 20 down. And then what do we do with these two moments that are also at that same spot? Add them up, yeah. So our new system is a 20 down, and I'll just draw it up here. And then what's the resolution of the couples? We have 250 going one direction, and we have 60 going the other. Is that correct? Yeah, so that's what, 190. Yeah, I'm doing it in my head, so that's always scary. 190 in the blue direction, which was what? This way? 190 foot-pounds. The point is, we went from this system, oh, how's it doing that? Oh, there it went. That's weird. We went from this system where we have two forces out here on our system to no more two forces. They're all gone. And now we have a force couple here. Okay? So we can make these force couples and move forces around. The point is to move them to the same spot and to collect those effects so we have an idea of what the heck's going on. Okay? Okay so far? All right, let's do, you want to do the final step, which would be, this would be like running the whole thing, but then we can fall back and do something else. But then they say, well, then we're going to do reduction of this force couple. After you collect it all in one spot, we want to reduce it back out to the effect on the structure, right? If this is a beam or a bridge or whatever the heck it is, we want to get to where we have something out here that then we can do future analysis on, right? Instead of 30 vectors, we want one vector on the system that is equivalent to the 30, right? So for us, instead of 2 vectors on the system, the 50 and the 30, we now have a 20 and 190 foot-pound rotation clockwise. So this is our force, and this is our couple. The final step is to distribute your force back out onto the system, which means this is your force, your resultant. Granted, we did a really easy one. It was just vertical, right? But you can think about if you had forces at angles, then you would end up with a bit more of a mess at your point that you choose. You know, you could have x's and y's, and then you got to like boil that down to a resultant, and then use that resultant and distribute it back out. So right now we have a pretty simple system where our resultant is this 20, correct? So it's going to be out here somewhere. I just don't know where. But I do know that the moment is equal to the force times the distance, and I know the moment, right? And I know the force. So I want to know this distance. What is that? So I can do that, right? 190 foot-pounds is equal to, what's my force? 20 times the distance. And I should be able to get that distance. Anyone got a number for me? 9.5 feet. That's where it is. Now, keep in mind, the 20 pounds is the total effect. It's not really a force, like it didn't exist in our first little thing, right? We had 50 and 30. There's no 20-pound force here. It's not there. It's the effect of the 50 and the 30. So this force is the resultant effect of all the forces that were going on. Does that make sense? And this distance is the resultant moment that was associated with that resultant effect. So both of these are effects that this system is feeling. This is if we want to get it back out onto the structure. Okay? That's how we go from one force, boil it, or from many forces, boil it all down to one force. How did I know? I just randomly moved it to the right. How did I know to move it to the right? Anyone want to wager a guess on that one? Because that's a good idea. That's what's positive? Get a little more detail there. Like because you can collect these forces anywhere. Like I could have picked a spot here to collect it, and I would have ended up with something like this, right? It could be in the middle of the system that you collect the forces. So you got to know, like, I got to move this thing somewhere. How do I know which way to go? The moment tells you which way to go. You have to create this moment. Meaning that if I move this force this way and place it out here, what kind of a moment do I create about that point? The same directional moment. Does that make sense? Like if I'm going to move this one, I don't even need numbers. I can just look at the diagram and I know which way to move this. Which way? I have to create that moment. It's got to go over here somewhere, because that's the only spot that creates the same rotation. If I moved it over here, what kind of rotation would it create? The wrong direction. So the rotation of the moment tells you which way to move your resultant to get it out on the system. Okay? All right. Why? Like, why are we doing this? What's the point? In the future, you're going to want bending stress. That's strength of materials. You haven't had strengths yet, right? Yeah. So that's strength of materials. You're going to want to be able to calculate bending stress. And from this, I can't calculate bending stress. I don't even know what the bending force is. I need to know the bending force, right? Bending force. Just found it. And where it's at. That's important. Like, is it in the middle of the span? That's a lot of deflection. Is it near a support? That's less deflection. Okay, so in the future, you're going to want to be able to boil these force systems down into a single resultant. That's why we do it. All right, let's do another one. Let's just do a practice one. Kind of start to finish, because we covered 3 sections right there. Like, that was a lot. All right, let's do the flagpole. Right, and we're going to bury our flagpole. And I'm going to put a couple forces on it. I keep using the word couple for a variety of reasons. I'm going to put a few forces on it. We're going to put this one on at 400 pounds. And we're going to say it's at 45 degrees. And then we'll put a nice... So maybe there's a number of cables up there, right? There might be 3 going each direction, but I'm going to kind of just do that in my head and keep this nice and clean. We'll put a resultant of 100 up there, horizontal. So you have 2 forces on the system, and we're going to say it's like 40 feet here and 40 feet here. So, if I'm going to be the telephone pole engineer, power pole engineer, I need to know what the effect is on this thing. Like, this is great, and I have all the forces collected, but I want to know what the single effect is on the pole. Like, what is the final force that it feels, and what its final rotation that it feels, okay? That's what I need to know to then calculate how big of a pole I need to carry that bending stress and all of those other things I got to think about, all right? So given this system, we want to take it to a single force on the pole, okay? So let's work through that together in steps. What do we do first? Yeah, pick a point. Kind of the same thing, like where are we working towards? So let's just pick this point down here. I'll call it A. Let's collect our forces down there. Let's move the easy one first. That's this one, the 100 pounds. So you guys can work on that. I'll give you a few minutes. So the flow here is pick a spot, move the forces to that spot, sum up the forces, sum up the couples, and then redistribute it back out. They did not use the word redistribute. They use, what is that? Simplify. Simplify the force couple system. Move the 100 first. That's the easy one. Draw the little couple in for me so you can see it. So you understand which forces get used and which ones stay. All right, if we're going to move the 100, what do we do down here at A? 100 going in both directions. And then which two create the couple? The opposite directed ones, those two. Ends up to be 100 times the distance apart, 80 feet, 800 foot. Oh, 8,000, thank you. That's why you don't do it in your head, right? That's why you use a calculator. Counting zeros is difficult. Which way does it rotate? Yeah, it's clockwise. So that goes in like this. So that 100-pounder is going to be the black pin.
Okay, so when you're turning, like, this clockwise, it kind of-
Yep.
we look at the original.
You look at the couple, the two that are being created. So like if I pulled them out, it's this one and this one. A lot of times I'd like in my head pull them out and kind of set them close to each other, and I get a better feel for spin than if they're like, you know, way up here and way down here. But it's these two, right? It's this one and this one, because they have to be oppositely directed, a distance apart, same magnitude, blah, 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 right? And then I just position myself in between and say, oh, if I'm going to hang on to these and let go of it, it's going to go that way. That's how I do it.
I was confused because those were A.
Yeah, so I just kind of position myself between the two, like up in here somewhere. This one and this one is going to go. Yeah. All right. The 400. How do you want to move that one? Yeah, you can break it into the components and then look for a couple, right? That's an easy way to do it. Or you could do trigonometry and try and come up with a distance. So if you're going to break it into its components, then you go here and here. When you go to move it, right, then you put in the component magnitude and the components down here, and you create those couples, okay? So what's this component equal to? Sine or cosine 45, right, times the 400. Anyone have that number? No calculator, sorry. Not on my phone. Say again? 283. It's probably not perfect, right? So is that 283 rounded?
Yeah.
What's the unrounded number?
282.843.
282.843, and that keeps going. So you don't want to do any rounding in the process, right? You want to round at the very end. So we would carry those out. So same kind of process. If I have this and this at 282.843, then I put in my oppositely directed 282.843 vectors, and I make a couple between two of them, and I figure that couple out. So that's going to be 282.843 times what distance? The distance apart? Yep, 40 feet, perfect. That was like 11,313. Yeah, and its rotation would be around that way. The same direction as the other one. 11,313.72, and that keeps going. Again, just reminding myself not to round as I'm going through it. So, as you can see, that diagram gets busy right away. Just think if you had multiple force, more than two. It gets quite crazy, so I continually draw a new picture. I'm actually working this out. This is gone. I do have the 100 left over down here. So I'm just going to start to collect everything down here at my point A. And then this one was 8,000. And then I just moved the 282.843. I used these two vectors, so that left this one still hanging out. 282.843. And then I had to add, yep, sorry. I had to add this next rotational effect of 11,313.72. I still haven't done anything with this critter. Anyone know what we can do with this thing? Can't really make a couple. I could add two down here, but there's no distance between them, right? This component, we can't forget about it. Still here. Anyone know how we can get it down here? Principle of transmissibility. I don't know if he actually talked about that principle, but along its line of action, you can just move vectors, right? It's on its line of action. It's supposed to be. I know I'm a little bit off of the depth of the pole, but we don't have a diameter of the pole. All right, so this just moves down. This 282.843 just comes down here and transfers down. 282.843. Now this is looking like a little more realistic problem. They almost always have X forces, Y forces, and moments when you do your force couples, right? If you do components, which I recommend, then at least you end up with X's and Y's at your point, and you can just add them up to get a resultant X and a resultant Y. And then from that, you can just Pythagorean theorem out the resultant force, right? So that's, I think, the way to go if you have forces at angles, splitting them into their components, ending up with X's and Y's. In this case, we only have one Y. But they're easy to add then when they're there, right? Because now we have this little kind of concurrent force system where we just add vectors up. Same with the moments. The moments are at the same spot, so we add those up. So we should be able to then, here's my pole again, and my point A. We should end up with one moment. That's going to be the combination of the 11,000 and the 8,000 to give me what? Trying to do it in my head, 19,313.72. Tell me I did that right.
You did it right.
Oh, good. 11,000 plus 8,000. I know. This is a higher level math class. Just got to be careful with it. Very careful. All right, so then what happens with my X vectors? Same thing, I add them up, right? But one's going positive, one's going negative, so I should end up with how much? Again, higher level math. I got this. 182.843. Took the 100 away from the 282. Yeah? Did I do that right? Nobody's verifying with their calculators, so I think we're all just going for it. All right, good, good. And then, of course, we didn't do anything with this creature. I'll make it blue. It's just hanging out here, 282.843. Good? Everyone kind of see how that worked? Now, we do have to resolve these to get the resultant, like the single force on the system, then you have to resolve these two into its resultant. But you all are experts at that, right? Pythagorean theorem, square this, add it together, then what? Take the square root of, yeah. So we're going from here down to here. What's our number? 336.8. And those are pounds, because this is a force. And then I have my 19,313.72 foot-pounds. So we've gone from this, 100 way up here, 400 here, to this, our force couple. That's the resultant. The pole in the ground feels this force acting on it at some point somewhere on the pole. How do I know where it is? I have to create this kind of rotation. Is that correct? And if you want to know where it's at, then you got to take, so remember, the moment is equal to the force times the perpendicular distance. If you use this force, then you're getting a distance perpendicular to it. So it's common when you end up with the resultants that are at an angle that you go back a step and say, okay, if I want to know where it is along this line of action, then you got to figure out like where it is, right? You can use the x component, because does the y component create anything to do with the moment? No. So yeah, you can just divide by the x component in a telephone pole problem, and on a bridge problem you can just divide by the y component, because that's the perpendicular distance. Okay? This is important because this is the final resultant effect. But these two are equally important because one of them is down force and one of them is side force. And those are very important in our analysis. Probably more important than this. These are the two that you typically would use. Okay? So to go from forces to force couple, back to force. What do you think? Make sense? Make some sense? Make a little sense? Yeah, when you go to work it, you'll probably be like, what did we do? So you might want to review this. Because it does get complicated. Yeah, it makes sense right now. As soon as you walk away and have a piece of pizza and then try it again, all of a sudden it doesn't make sense. So maybe go for salad or something. All right, so now I have to figure out how to push stop. Got it.